Let's talk about cold. Not the kind of cold where you pull a blanket tighter around your shoulders, or where you can see your breath hanging in the air on a January morning. I mean real cold. The kind of cold that exists at the very edge of what's physically possible. The kind of cold where atoms themselves almost forget how to move. Where matter starts behaving in ways that would seem like pure magic to anyone who hasn't spent years studying physics. Where the rules you've known your whole life, the ones about how things flow and resist and vibrate, just quietly stop applying. There's a number at the bottom of every thermometer, a number that sits there like a floor beneath everything else. 0 on the Kelvin scale, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. Absolute zero. And here's the thing that makes it so fascinating, so strange, so endlessly compelling to physicists. You can never actually get there. Not in practice. Not even in theory. The universe itself won't let you. No matter how clever you are, no matter how sophisticated your equipment, no matter how many billions of dollars you throw at the problem, you cannot cool anything down to absolute zero. You can get breathtakingly, astonishingly close. You can reach temperatures so cold that they make the vacuum of deep space look like a summer afternoon. But that last tiny, infinitesimal gap between where you are and true zero, it stretches out forever, like a hallway that gets longer the closer you get to the door at the end. And tonight, that's what we're going to explore together. Why that floor exists, what temperature actually is when you strip away all the everyday assumptions, how scientists spent centuries racing each other to get colder and colder and colder, and what they discovered along the way about the deepest nature of matter and energy. It's a story full of rivalry and obsession and beautiful physics, and it ends. Well, it doesn't really end. That's kind of the whole point. So let's start with something simple, something you think you understand, but probably don't. Not fully. What is temperature? You feel it every day. You know when something is hot, you know when something is cold. You know that a cup of tea cools down if you leave it on the counter, and that ice melts if you leave it on the table. Temperature feels like one of the most basic, most intuitive things in the world. But here's the thing. What you're actually feeling, what temperature actually is something much deeper and stranger than it seems on the surface. Temperature is motion. That's really it, at the most fundamental level. Temperature is a measure of how much the tiny particles that make up everything, atoms, molecules, are jiggling around. When something is hot, its atoms are moving fast. They're vibrating, rotating, bouncing off each other with tremendous energy. When something is cold, those same atoms are moving more slowly. They're calmer, more subdued, less frantic in their microscopic dance. Think about the air in the room around you right now. It feels still, doesn't it? Like nothing's happening. But down at the molecular level, it's absolute chaos. Nitrogen molecules and oxygen molecules are zipping around at something like 500 meters per second. That's faster than a bullet, slamming into each other billions of times every second, ricocheting off the walls, off your skin, off everything. The temperature you feel, the warmth or coolness of that air, is just a reflection of how fast those molecules are going on average. Warm them up, and they move faster. Cool them down, and they slow down. Now, that idea, temperature as motion, wasn't always obvious. For most of human history, people thought of heat as a substance, something that flowed from hot objects into cold ones, like water flowing downhill. They called it caloric, and it was a perfectly reasonable theory. It explained a lot of everyday observations. Hot things have a lot of caloric. Cold things have a little. And caloric naturally flows from where there's more to where there's less. When you put a hot iron in cold water, the caloric flows from the iron into the water, and the iron cools down while the water heats up. Simple, intuitive, and wrong. The caloric theory held sway for over a century, from the late 1700s well into the 1800s. It was championed by some of the biggest names in science. Antoine Lavoisier, the father of modern chemistry, was a big believer, and it worked pretty well for a lot of practical purposes. But it had some problems that nagged at a few sharp minds. One of those minds belonged to Benjamin Thompson, an American-born scientist and adventurer who later became Count Rumford. Long story, involving espionage, fleeing the American Revolution, and marrying into Bavarian nobility. In the 1790s, Rumford was supervising the boring of cannon barrels in Munich, and he noticed something that didn't fit the caloric theory at all. The friction of the boring process generated enormous amounts of heat, seemingly limitless amounts. As long as you kept boring, the heat kept coming. If heat were a substance, a finite fluid contained within the metal, it should eventually run out, but it never did. Rumford concluded that heat wasn't a substance at all. It was motion, mechanical work. The energy of grinding metal against metal was being converted into heat. This was a radical idea, and it took decades to be fully accepted. But Rumford was right. Heat is not a thing. It's a process. It's the transfer of kinetic energy from fast-moving particles to slow-moving ones. And temperature is a measure of how much of that kinetic energy the particles possess. This insight, that heat is motion, was eventually nailed down rigorously by James Prescott Joule in the 1840s through a series of meticulous experiments measuring the mechanical equivalent of heat. Joule showed that a precise amount of mechanical work always produces a precise amount of heat. The two are interconvertible. Energy is conserved. This became the first law of thermodynamics. Energy can be transformed from one form to another, but it cannot be created or destroyed. And that brings us to the question that matters for our story. If temperature is atomic motion, and cooling something down means slowing those atoms down, then what happens if you slow them down all the way? What happens if you remove every last bit of motion, every last shred of kinetic energy, until the atoms just stop? That's absolute zero. That's the idea. The temperature at which all atomic motion ceases completely. The bottom of the thermometer. The coldest anything could theoretically be, because you can't go slower than stopped. You can't have less motion than no motion at all. Makes sense, right? It's a clean, elegant idea. And for a long time, that's how people thought about it. There's a lowest possible temperature, and in principle, you could reach it if you were clever enough. You'd just need to keep removing energy until there was nothing left to remove. But nature, as it turns out, is far more subtle than that. And the story of how we figured that out, how we discovered that absolute zero isn't just hard to reach, but actually impossible to reach, is one of the great intellectual adventures of modern physics. It touches on thermodynamics, quantum mechanics, information theory, and the very structure of reality itself. And it starts, as so many stories in physics do, with someone asking what seems like a very practical question. Let's go back to the early 1800s. This is the age of steam. The Industrial Revolution is roaring across Europe, and the big question on everyone's mind isn't about the nature of reality. It's about engines. How do you build a better engine? How do you get more work out of a given amount of coal? How do you make machines more efficient? Enter Sadi Carnot, a young French military engineer, brilliant and quiet, the son of a famous politician and mathematician. Lazare Carnot, his father, had been one of the leading figures of the French Revolution and a gifted geometer in his own right. So young Sadi grew up surrounded by both political upheaval and mathematical rigor. He studied at the École Polytechnique in Paris, which was at the time perhaps the finest scientific institution in the world, and then joined the army as an engineer. But his heart was in physics. In 1824, Carnot published a slim little book called Reflections on the Motive Power of Fire. It's one of the most important scientific works ever written, though almost nobody read it at the time. Carnot was interested in a very specific question. What's the maximum amount of useful work you can extract from a heat engine? An engine that takes in heat from a hot source, converts some of it into work, and dumps the rest into a cold sink. That's basically what every engine does, from a steam locomotive to a car engine to the turbines in a power plant. Hot source in, work out, waste heat dumped somewhere cooler. And Carnot figured out something remarkable. He showed that the maximum efficiency of any heat engine depends on just two things: the temperature of the hot source and the temperature of the cold sink. That's it. Doesn't matter how the engine is built, what fuel it uses, how clever the design is. The maximum possible efficiency is determined entirely by those two temperatures. And here's the crucial part. The closer the cold sink is to absolute zero, the more efficient the engine can be. If you could actually reach absolute zero for your cold reservoir, you could build a perfectly efficient engine, 100% of the heat converted to work, with no waste at all. But Carnot also realized, even in that early work, that something about this was problematic. A perfectly efficient engine seemed to violate something deep about how the universe works. It was a hint, just a whisper really, that absolute zero might be special, that it might be unreachable. Now, Carnot died young, tragically young, just 36 years old, carried off by cholera in 1832. Most of his papers were burned, as was the practice with the belongings of cholera victims, to prevent the spread of disease. We'll never know what else he might have discovered, but his published work planted a seed that would grow into something enormous. Because a few decades later, two men, working independently, approaching the problem from completely different angles, would take Carnot's insights and forge them into one of the most powerful and profound frameworks in all of science: thermodynamics. The first was Rudolf Clausius, a German physicist with a gift for seeing the mathematical structure hidden inside physical processes. In the 1850s, Clausius took Carnot's work and sharpened it to a razor edge. He introduced a concept that would become one of the most important and most misunderstood ideas in all of physics: entropy. Now, entropy is one of those words that gets thrown around a lot, often incorrectly, and it's worth taking a moment to really understand what it means, because it's going to be central to our story. Entropy, at its core, is a measure of disorder, or more precisely, it's a measure of how many different microscopic arrangements of atoms and molecules are consistent with what you observe on the large scale. That sounds abstract, so let me give you an analogy. Imagine you have a deck of cards. A brand new deck, still in order, aces through kings, each suit neatly arranged. That's a very low entropy state. There's really only one way to arrange a deck so that it's perfectly sorted. Now shuffle that deck. Each shuffle increases the entropy, because now there are more and more possible arrangements that look equally random to a casual observer. A shuffled deck has high entropy. There are billions upon billions of different specific arrangements that would all look equally disordered if you fanned them out on a table. Here's the important bit. If you shuffle a sorted deck, you will essentially always get a disordered one. But if you shuffle a disordered deck, you will essentially never get a sorted one. Not because it's impossible. It's just so overwhelmingly unlikely that you'd need to shuffle for longer than the age of the universe to have a decent chance. Disorder is overwhelmingly more probable than order, simply because there are so many more ways to be disordered than to be ordered. Temperature and entropy are deeply connected. When you heat something up, you're increasing the number of ways its atoms can be arranged. You're giving them more energy, more speed, more options for how to move and vibrate. You're increasing the entropy. When you cool something down, you're reducing those options. You're constraining the atoms, giving them fewer ways to behave. You're decreasing the entropy. And here's where Clausius dropped a bombshell that changed everything. He formulated what we now call the second law of thermodynamics. And it says essentially that in any natural process, the total entropy of the universe never decreases. It can stay the same in an idealized reversible process. But in any real process, entropy always goes up. Disorder always increases. Things always tend toward equilibrium, toward the most probable arrangement, toward the most mixed up, spread out, disordered state. Think about what that means. A hot cup of coffee left on a counter will always cool down. It will never spontaneously heat up by drawing energy from the cooler air around it. Why not? Because that would decrease the total entropy. The heat spreading out from the coffee into the room increases disorder. The energy gets distributed among more and more molecules, spread out more evenly. The reverse process, all that spread out energy spontaneously concentrating back into the coffee, would decrease entropy. And the second law says that doesn't happen, not because it violates conservation of energy, it doesn't, but because it's so overwhelmingly improbable that it essentially never occurs in the lifetime of the universe. Now, around the same time Clausius was working out entropy, another brilliant mind was circling the same ideas from a slightly different direction. William Thomson, later known as Lord Kelvin, was a Scottish-Irish physicist who was obsessed with the idea of an absolute temperature scale. See, the existing temperature scales, Fahrenheit, Celsius, were arbitrary. They were based on things like the freezing and boiling points of water, which are useful but not fundamental. Thomson wanted a scale grounded in physics itself, one that started at the absolute bottom, at the point where no more heat could be extracted from a system. In 1848, Thomson proposed exactly that, the Kelvin scale. 0 Kelvin was the bottom, absolute zero, and the degrees were the same size as Celsius degrees, so water freezes at 273 Kelvin and boils at 373 Kelvin. But the crucial thing was where zero was. 0 Kelvin wasn't just an arbitrary point on a scale. It was the point where, in theory, all thermal motion stops, the absolute floor of temperature. And Thomson, like Carnot before him, sensed that this floor was special, not just a number, but a kind of boundary, a place you could approach but never quite reach. He wrote about it with something close to reverence, this idea that the natural world had a built-in lower limit, a boundary that no ingenuity could cross. But coming back to our story, let me tell you about Ludwig Boltzmann, because his contribution is essential, and his story is one of the most heartbreaking in all of science. Boltzmann was an Austrian physicist working in the late 1800s, and he was the one who truly explained what temperature and entropy mean at the deepest level, not as vague notions about disorder or randomness, but as precise, mathematical, countable properties of systems made of enormous numbers of particles. Boltzmann's great insight was that the macroscopic properties we observe, temperature, pressure, entropy, are not fundamental in themselves. They emerge from the collective behavior of trillions upon trillions of atoms, the way a crowd surge emerges from the movements of individual people who are each just trying to get to their seat. No single atom has a temperature. Temperature is a property of collections, of ensembles, of vast numbers of particles whose individual behaviors average out into the smooth, predictable quantities we measure with thermometers. He expressed this mathematically with what might be the most profound equation in all of physics. It's carved on his tombstone in the Zentralfriedhof Cemetery in Vienna. S equals K log W. Entropy equals Boltzmann's constant times the natural logarithm of the number of microstates. This equation connects the macroscopic world of temperature and heat to the microscopic world of atoms and probability, and it does so with breathtaking elegance. Let me unpack that, because it's crucial for understanding absolute zero. W, the number of microstates, is a count. It's the number of different ways you could arrange all the atoms in a system so that the system still looks the same from the outside, still has the same temperature, the same pressure, the same volume. At high temperatures, W is enormous. There are mind-bogglingly many ways the atoms could be arranged that would give you the same macroscopic properties. At low temperatures, W shrinks. There are fewer and fewer configurations available to the atoms as they slow down and their options narrow. And at absolute zero, for a perfect crystal, W equals 1. There's only one way to arrange the atoms, every single one in its correct position in the lattice, every quantum number at its minimum value. Log of 1 is 0, so S, the entropy, is 0. Perfect order, complete certainty about the microscopic state, zero information missing. Now, here's what makes Boltzmann's story so tragic. His ideas were ahead of their time. In the late 1800s, many prominent physicists, including Ernst Mach and Wilhelm Ostwald, didn't believe atoms were real. They thought atoms were a useful mathematical fiction, a bookkeeping device, not actual physical objects. And Boltzmann's entire framework depended on atoms being real. His statistical mechanics only made sense if matter was actually composed of discrete, countable particles. Boltzmann spent years defending his ideas against fierce, often personal attacks. The debates were brutal. Mach, in particular, was relentless, dismissing Boltzmann's work as misguided and speculative. Boltzmann, who suffered from what we would now probably diagnose as bipolar disorder, was deeply affected by the criticism. He felt increasingly isolated and unappreciated. In 1906, the same year Nernst published his heat theorem, the same year physics was about to vindicate everything Boltzmann had argued for. Boltzmann hanged himself while on holiday with his family in Duino, near Trieste. He was 62 years old. It's one of the great tragedies of science. Within just a few years of his death, Einstein's work on Brownian motion and Jean Perrin's experiments confirmed the reality of atoms beyond any doubt. Boltzmann had been right all along. His statistical mechanics became one of the pillars of modern physics, and his equation, S equals K log W, became one of the most fundamental relationships in science. But he never lived to see his vindication. Think about that for a moment. The man who explained what temperature really means, who provided the mathematical framework that would eventually prove why absolute zero is unreachable, who connected the world of everyday experience to the invisible world of atoms. That man died, believing his life's work had been rejected. Science can be cruel, but the ideas endure, and Boltzmann's legacy is immeasurable. But the person who really nailed this down, who proved, mathematically and physically, that absolute zero is genuinely unreachable, was a German chemist named Walter Nernst. And his story is one of the most underappreciated chapters in the history of science. Nernst was a fascinating character, stocky, intense, with a walrus mustache and a personality that could generously be described as abrasive. He was brilliant, and he knew it, and he didn't particularly care if that rubbed people the wrong way. He made his fortune inventing an electric lamp, the Nernst lamp, which used a ceramic rod instead of a filament and was briefly a serious competitor to Edison's incandescent bulb, and spent his money on fancy cars and a country estate where he raised carp. He was one of those rare scientists who was equally comfortable in a laboratory and in a boardroom, and he had an ego to match. There's a wonderful story, possibly apocryphal, but telling either way, about Nernst attending a conference where another scientist presented a new theory. When asked his opinion, Nernst reportedly said, "That theory is not even wrong," meaning it was so poorly formulated that it couldn't even be tested. It's the kind of cutting remark that makes you understand both his brilliance and why so many of his colleagues found him difficult. In the early 1900s, Nernst was working on a problem in physical chemistry, trying to understand how chemical reactions behave at very low temperatures, and he noticed something that didn't quite fit the existing framework. When he extrapolated the thermodynamic properties of substances down toward absolute zero, the entropy changes in chemical reactions seemed to approach zero. Not just get small, approach zero precisely, consistently, regardless of the specific reaction or materials involved. This led him, in 1906, to propose what he called his heat theorem. It would eventually become known as the third law of thermodynamics. And what it says, in its most general form, is this: as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum value. For a perfect crystal, a perfectly ordered solid with every atom in exactly the right place, that minimum value is zero. Now, that might sound like a technical detail about crystals and chemistry, but its implications are staggering. Because if the entropy of a system approaches zero as the temperature approaches zero, then removing the last tiny bits of heat from a system becomes progressively harder and harder. You need to do more and more work to extract less and less heat. The process of cooling down doesn't just get difficult near absolute zero. It becomes asymptotically impossible. Each halving of the remaining temperature requires more effort than the last. The closer you get, the more the universe pushes back. Let me try to give you an intuition for why this is. Because it's one of those ideas that sounds straightforward in words, but is genuinely profound when you feel it in your gut. Think about cooling something down as a process of removing energy from it. At high temperatures, there's a lot of energy to work with. The atoms are jiggling wildly, and it's relatively easy to extract some of that energy. You can use any number of techniques. Let it radiate heat, put it in contact with something colder, blow cold air over it. There's plenty of energy to grab, plenty of fast-moving atoms to slow down. But as you cool something down, there's less and less energy left. The atoms are moving more and more slowly, and now you need to find a way to extract the little bit that remains. But here's the catch. Any process you use to cool something down involves some kind of energy exchange with the environment, and that environment is never perfectly ordered. There's always some stray thermal energy, some slight disturbance, some irreversible process that adds a tiny bit of heat back in, even as you're trying to remove it. It's a bit like trying to empty a bathtub with a leaky bucket. At first, when the tub is full, you're making great progress. Bucket after bucket, the water level drops steadily. But as the tub gets nearly empty, the leaks in the bucket start to matter more and more. Each trip to the tub picks up a little less water, and the leaks let some dribble back in on the way to the drain. And the closer you get to truly empty, the more the leaks matter relative to what you're carrying. You can get the water level incredibly low. But perfectly empty, the bucket won't let you get there. That analogy isn't perfect, they never are, but it captures the essential frustration. Every cooling technique has its own version of that leaky bucket, some fundamental limitation that prevents it from reaching zero. And this isn't just engineering. This isn't just about needing better equipment or a bigger budget. The third law tells us that this impossibility is built into the fabric of physics itself. It would take an infinite number of steps to reach absolute zero, which means, since we don't have infinite time or infinite resources, we can never get there, period. But that hasn't stopped people from trying to get close. And the history of that attempt, the great race toward absolute zero, is one of the most thrilling, most competitive, most obsessive chapters in experimental physics. It's a story of brilliant scientists, lethal explosions, liquefied gases, and temperatures that make the coldest corners of outer space seem warm by comparison. Let's go back to the 1800s once more. By the middle of that century, scientists knew about absolute zero as a theoretical concept, but the coldest temperatures anyone had actually achieved in a laboratory were, by modern standards, pathetically warm. The big challenge of the era was liquefying gases. See, every substance has a temperature at which it transitions from gas to liquid, its boiling point. For water, that's 100 degrees Celsius. For ethanol, 78. For oxygen, it's minus 183. For nitrogen, minus 196. The lower the boiling point of a gas, the harder it is to liquefy, because you have to cool it down further. Michael Faraday, the great English experimentalist, the same Faraday who discovered electromagnetic induction and basically invented the electric motor and the generator, was one of the first to seriously tackle gas liquefaction. Faraday is one of those people who, the more you learn about, the more impressed you become. He had almost no formal education. He was a bookbinder's apprentice who taught himself science by reading the books he was binding. He got his start in science by attending lectures by the great chemist Humphrey Davy at the Royal Institution in London, taking meticulous notes, binding them into a book, and sending them to Davy as a calling card. Davy was so impressed that he hired Faraday as his laboratory assistant. Within a few years, the assistant had surpassed the master. In the 1820s, and again in the 1840s, Faraday managed to liquefy a number of gases by compressing them and cooling them simultaneously. Chlorine, carbon dioxide, sulfur dioxide, hydrogen sulfide, nitrous oxide. He turned them all from gas to liquid, one by one. It was beautiful work, careful and systematic, and it opened up an entirely new field of research. But some gases resisted. Oxygen, nitrogen, hydrogen, carbon monoxide, methane, and helium, the so-called permanent gases, refused to liquefy no matter how much pressure Faraday applied. For decades, scientists thought these gases might be truly permanent, that they simply couldn't exist as liquids. It was a reasonable guess, but it was wrong. It wasn't until the 1860s that an Irish physicist named Thomas Andrews figured out why they resisted. He discovered the concept of the critical temperature. For each gas, there's a temperature above which no amount of pressure will liquefy it. You have to cool the gas below its critical temperature first, and then you can compress it into a liquid. The permanent gases just had critical temperatures that were far lower than anything anyone had achieved at the time. Oxygen's critical temperature is minus 118 Celsius. Nitrogen's is minus 147. Hydrogen's is minus 240. And helium's critical temperature is minus 268 Celsius, just 5 degrees above absolute zero. That's why helium was the last holdout. This discovery set off a race. An international, decades-long, fiercely competitive race to liquefy the permanent gases. And the stakes were high, not just for practical applications, but for the fundamental understanding of matter. What happens to substances at extremely low temperatures? Do the laws of physics change? Does matter behave differently? Nobody knew, and the only way to find out was to get colder. In 1877, two scientists, Louis-Paul Cailletet in France and Raoul Pictet in Switzerland, independently managed to produce tiny amounts of liquid oxygen for the first time. Kayate used a technique called adiabatic expansion, compressing a gas and then suddenly releasing the pressure, which causes the gas to cool rapidly as it expands. He saw a brief mist of liquid oxygen droplets appear in his apparatus. It was fleeting, just a momentary fog, but it was real. You can imagine the excitement, seeing for the first time ever a substance that exists as a gas in everyday life transform into a liquid, a shimmering blue liquid with an eerie, otherworldly quality. Meanwhile, Pictet used a cascade method, cooling one gas with another, using each liquefied gas as a stepping stone to cool the next one down further. These were landmark achievements, but they were just the beginning. The next target was nitrogen, then hydrogen, and finally, the ultimate prize, helium. Now, let me tell you about James Dewar, because he's one of those figures in the history of science who was absolutely brilliant and absolutely impossible to work with. A Scottish chemist and physicist who became obsessed with low-temperature research. He's the one who invented the Dewar flask. You know it better as a thermos. That vacuum-insulated container that keeps your coffee hot or your iced drink cold. Dewar invented that specifically to store liquefied gases. He needed a way to keep his liquid oxygen and liquid air from boiling away, and he came up with this elegant solution of a double-walled glass vessel with the air pumped out from between the walls, so there was nothing to conduct heat across the gap. It was brilliant in its simplicity, and it's still the basic design used in thermoses today, over 130 years later. Dewar spent the 1890s pushing temperatures lower and lower. He was relentless. In 1898, he achieved something spectacular. He liquefied hydrogen. By using a cascade of cooling stages and then expanding the hydrogen gas through a valve, a technique refined by the work of James Joule and William Thomson, now called the Joule-Thomson effect, he managed to produce liquid hydrogen at a temperature of about 20 Kelvin. That's 20 degrees above absolute zero, minus 253 Celsius, the coldest temperature ever achieved by a human being at that time. He collected it in his vacuum flasks, and for a brief period, his laboratory at the Royal Institution in London was the coldest place in the known universe. But Dewar wanted the big prize. He wanted to liquefy helium. And here's where the story takes a dramatic turn, because Dewar wasn't the only one chasing that goal. On the other side of the English Channel, in the Dutch city of Leiden, there was another physicist with the same ambition. His name was Heike Kamerlingh-Onnes, and he was, in many ways, Dewar's opposite. Where Dewar was volatile, secretive, and prone to feuding with colleagues, Kamerlingh-Onnes was systematic, collaborative, and methodical. Where Dewar worked in fits of inspiration and guarded his techniques jealously, Kamerlingh-Onnes built an entire laboratory, an entire institution, designed specifically for low-temperature research. His motto was, Door meten tot weten, through measurement to knowledge. His lab in Leiden became the coldest place on Earth, and he staffed it with the best instrument makers and glassblowers he could find. The race between Dewar and Kamerlingh-Onnes to liquefy helium was one of the great scientific rivalries of the era. Helium was the last holdout, the gas with the lowest boiling point of any element, just 4.2 Kelvin above absolute zero. To liquefy it, you'd need to cool it below that temperature, which meant reaching colder than anything anyone had ever achieved. Dewar came tantalizingly close. He had the expertise, he had the equipment, he had the raw talent. But he also had a catastrophic weakness. He kept blowing up his apparatus. I'm not exaggerating. Dewar's lab suffered a series of devastating explosions and accidents in the early 1900s that destroyed equipment, injured assistants, and set his research back years. Hydrogen gas, when mixed with air, is extraordinarily explosive. It's what brought down the Hindenburg. And Dewar was working with huge quantities of it. One explosion in 1901 destroyed a vacuum pump that had taken months to build. Another shattered an entire cooling apparatus. His assistants lived in fear. Several quit. Meanwhile, in Leiden, Kamerlingh Onnes was methodically solving every technical problem one at a time. He built a massive gas liquefaction cascade, using liquid air to cool hydrogen, then liquid hydrogen to cool helium, each stage bringing the temperature lower. He trained a team of expert glassblowers and instrument makers. He was patient, meticulous, and relentless. Where Dewar's approach was heroic and chaotic, Kamerlingh Onnes's was industrial and systematic. On July 10, 1908, Kamerlingh Onnes and his team at Leiden finally did it. They liquefied helium. The temperature in their apparatus dropped below 4.2 Kelvin, colder than anything in the known universe, except for certain astronomical objects that hadn't been discovered yet. They had less than 100 milliliters of liquid helium, barely enough to fill a small teacup, but it was real. They'd reached a place on the thermometer that no human being had ever touched before. Dewar was reportedly devastated. He had been so close, and the explosions had cost him the prize. And this is where things get really interesting. Because once Kamerlingh Onnes had access to these extreme temperatures, he started exploring what happened to materials down there. He was systematically measuring the properties of metals and other substances at liquid helium temperatures, and what he found was completely unexpected. In 1911, just 3 years after liquefying helium, Kamerlingh Onnes was measuring the electrical resistance of mercury at very low temperatures. Now, everyone expected that as you cooled a metal down, its electrical resistance would decrease gradually. The reasoning was straightforward. Atoms jiggle less at lower temperatures, so they scatter electrons less, and electrons can flow through more easily. That was the standard picture. Maybe the resistance would approach zero smoothly, asymptotically, as you approached absolute zero. Maybe it would flatten out at some residual value. There was debate about which, but nobody expected what actually happened. At 4.2 Kelvin, right at the boiling point of liquid helium, the resistance of mercury didn't just decrease. It vanished, completely, abruptly. One moment there was measurable resistance, and the next moment there was none. Zero. Not almost zero, not very small, not approaching zero gradually. Zero. As if someone had flipped a switch. The mercury had become a perfect conductor. An electric current started in a loop of supercooled mercury would flow forever. Literally forever. With no resistance, no energy loss, no degradation whatsoever. Kamerlingh Onnes had discovered superconductivity, and he was stunned. Nobody had predicted this. Nothing in the existing theories of electricity and magnetism suggested that resistance should suddenly disappear at a specific temperature. It was as if the metal had undergone a phase transition, like water freezing into ice. But instead of changing from liquid to solid, it had changed from a regular conductor into something entirely new, something that conducted electricity with absolute, flawless perfection. Let that sink in for a second. At the temperatures you and I live in, every wire, every circuit, every conductor wastes some energy as heat. That's why power lines lose energy over long distances, about 5 to 10%, depending on the distance and the voltage. That's why your phone gets warm when you're using it. That's why computers need fans and heat sinks. Electrical resistance is everywhere, and it's always eating away at the energy flowing through a circuit, turning useful electrical energy into waste heat. But at 4.2 Kelvin, mercury just stops resisting. The electrons flow without any friction at all, like a ball rolling on a perfectly frictionless surface forever, never slowing down, never losing energy. Except this isn't a thought experiment or an idealization. It's real. It actually happens. Kamerlingh Onnes won the Nobel Prize in 1913 primarily for his work on liquefying helium and studying the properties of matter at low temperatures. The citation didn't even specifically mention superconductivity. The Nobel Committee focused on the broader achievement of reaching those extreme temperatures. But it was superconductivity that would prove to be his most lasting legacy. Superconductivity was just the beginning. As scientists developed better cooling techniques and reached ever lower temperatures, they discovered an entire zoo of strange phenomena that only appear near absolute zero. And one of the strangest and most beautiful is superfluidity. In 1937, two teams, Piotr Kapitsa in Moscow and John Allen and Don Misener in Cambridge, independently discovered that liquid helium, when cooled below about 2.17 Kelvin, transforms into something called a superfluid. And superfluids are unlike anything in ordinary experience. A superfluid has zero viscosity. Not low viscosity, zero viscosity. That means it flows without any friction at all. Let me try to convey how strange this is. Take honey. Honey is viscous, thick, slow, reluctant to flow. Water is much less viscous. It flows easily, pours quickly. Now imagine a substance that makes water look like honey. A substance so frictionless that it flows through channels too narrow for any normal liquid to pass. A substance that, once set in motion, will flow literally forever without stopping. That's a superfluid. If you put superfluid helium in a cup and spin the cup, the fluid won't spin with it. It'll just sit there, perfectly still, utterly indifferent to the rotation of the cup around it. If you put it in a container with tiny, microscopic pores far too small for any normal liquid to pass through, the superfluid will flow right through them as if they weren't there. Most bizarrely of all, it can climb up the walls of a container and flow over the rim, seemingly defying gravity. Put some superfluid helium in a beaker, and it will slowly creep up the inside walls, forming an incredibly thin film, flow over the top, down the outside, and drip off the bottom until the beaker is empty. It's called the Rowland film effect, and it's one of the most visually bizarre phenomena in all of physics. The first time you see it, even in a video, you can't quite believe it. And there's something even stranger. If you try to heat a superfluid, say by shining a light on it or touching it with something warm, instead of conducting the heat the way normal materials do, slowly and diffusively, it develops what are called second sound waves. These are temperature waves, literal waves of hot and cold that propagate through the fluid the way sound waves propagate through air. Normal heat conduction is diffusive. It spreads out slowly and evenly, like a drop of ink in a glass of water, blurring and spreading until everything is uniform. But in a superfluid, heat travels as a wave. It bounces off walls. You can reflect it, focus it, interfere it with other temperature waves. It's heat behaving like sound. That is deeply, profoundly strange. Both superconductivity and superfluidity are quantum mechanical effects that become visible at the macroscopic scale only at extremely low temperatures. At normal temperatures, quantum effects are hidden, washed out by all the thermal jiggling of atoms. The quantum world is there, governing everything, but its weirdness is masked by the noise of thermal energy. But as you cool a system down, strip away more and more of that thermal noise, the quantum nature of matter starts to show through. The atoms stop behaving like tiny billiard balls and start behaving like waves. Their quantum properties, which are always there but usually invisible, begin to dominate. And this brings us to something crucial. something that takes the question of absolute zero from a practical impossibility to a fundamental one. Quantum mechanics doesn't just make absolute zero hard to reach. It makes it meaningless in a certain deep sense. Because even at absolute zero, even in a state of minimum energy, particles don't actually stop moving. This is one of the most counterintuitive and beautiful results in all of physics, and it comes straight from the Heisenberg uncertainty principle. You've probably heard of it, the idea that you can't simultaneously know both the exact position and the exact momentum of a particle with perfect precision. The more precisely you pin down where a particle is, the less precisely you can know how fast it's going, and vice versa. This isn't a limitation of our instruments. It's not that our measurements are clumsy and disturb the particle. It's a fundamental feature of reality itself at the quantum level. Position and momentum simply don't have precise, definite values simultaneously. They can't. The universe won't allow it. Werner Heisenberg formulated this principle in 1927, and it was one of the key insights of the quantum revolution. Heisenberg was just 25 years old at the time, younger than many graduate students, and he was working at Niels Bohr's Institute in Copenhagen. The story goes that he was pacing the streets of Copenhagen late at night, trying to make sense of the mathematics of quantum mechanics, when the insight struck him. You can know where a particle is, or you can know how fast it's going, but you can't know both at the same time. The product of the uncertainties in position and momentum always has to be at least as large as a tiny constant, Planck's constant divided by 4 pi. Now, think about what this means for absolute zero. If a particle were truly at rest, completely motionless, then you'd know its momentum precisely. It would be zero. Exactly. Perfectly zero. But the uncertainty principle says you can't know the momentum precisely without having enormous uncertainty in the position. The more precisely the momentum is zero, the more uncertain the position must be. In the extreme case, the particle would have to be everywhere at once. And if it's confined in any way, trapped in a box, held in a crystal lattice, bound in an atom, then its position can't be infinitely uncertain. It has to be somewhere within that space, some range of positions. So the uncertainty principle creates a fundamental tension. A particle confined in space cannot have zero momentum. It's forced, by the very structure of quantum mechanics, to retain some minimum amount of motion. This minimum motion is called zero-point energy, and it's the irreducible minimum energy that a quantum system possesses, even at absolute zero. Let's sit with that for a moment, because it's profound. Even if you could somehow remove every single bit of thermal energy from a system, which the third law says you can't, the atoms would still be moving. Not because they're warm, not because there's some residual heat you failed to extract, but because quantum mechanics requires it. Motion is built into the very nature of particles. Stillness, at the quantum level, isn't just difficult, it's impossible. It would violate the uncertainty principle, and the uncertainty principle is not a suggestion, it's a law. The zero-point energy of most systems is tiny, so small you'd never notice it in everyday life. But it's real, and it has real, measurable consequences. It's the reason that helium remains a liquid all the way down to absolute zero at normal atmospheric pressure. Every other element, every single one, freezes into a solid if you cool it enough. But helium's atoms are so light, and their zero-point energy is so relatively large compared to the weak forces between helium atoms, that the quantum jiggling prevents them from settling into the rigid lattice of a solid. At normal atmospheric pressure, helium stays liquid forever, no matter how cold you make it. You need to squeeze it, apply about 25 atmospheres of pressure to force it into a solid. It's the only element with this property, and it's a direct, tangible, unmistakable consequence of zero-point energy. Now, I want to connect what we've been discussing to something even more fundamental. The zero-point energy I mentioned earlier, the irreducible quantum jiggling that persists even at absolute zero, is part of something bigger, something that reaches down into the very fabric of space itself. In quantum field theory, the framework that underlies our deepest understanding of nature, the theory that combines quantum mechanics with special relativity, empty space isn't empty, not even close. What we call the vacuum, the absolute void, is actually seething with activity. Quantum fields, the fields associated with every type of particle, are constantly fluctuating, even in their ground state, even when no particles are present. These fluctuations are real. They have measurable consequences. In 1948, the Dutch physicist Hendrik Casimir made a remarkable prediction. He calculated that if you place two uncharged metal plates very close together in a vacuum, close, meaning separated by a distance comparable to a wavelength of visible light, they would experience a tiny but measurable attractive force. Why? Because the vacuum fluctuations between the plates are constrained by the plate's boundaries. Only certain wavelengths of fluctuations can fit between the plates, while outside the plates, all wavelengths are allowed. This imbalance creates a slight pressure, pushing the plates together. It's as if the vacuum between the plates has slightly less energy than the vacuum outside, and the plates are pushed together by the difference. The Casimir effect was eventually measured with high precision in the late 1990s, and it confirmed exactly what Casimir had predicted. Empty space has energy. The vacuum pushes things around. Nothingness has measurable physical effects. And here's why this matters for absolute zero. Even if you cooled a system to absolute zero, which you can't, but hypothetically, the quantum fields filling all of space would still be fluctuating. There would still be vacuum energy, still zero-point fluctuations, still activity at the most fundamental level. You can remove all the thermal excitations. You can strip away every last phonon and every last quasiparticle, but you cannot remove the vacuum fluctuations. They're not excitations on top of something. They are the something. They're the ground state of reality itself, and you can't go below the ground state. This connects to something beautiful and profound. The unreachability of absolute zero isn't just about particles or atoms or crystals. It's about the nature of space itself. The universe, at its most basic level, is quantum, and quantum means fluctuating, always, everywhere, without exception. Absolute zero would mean absolute stillness, and absolute stillness is incompatible with a quantum universe. The two concepts are fundamentally, irreconcilably at odds. So when you ask, why can't we reach absolute zero? There are really two answers, and they reinforce each other beautifully. The thermodynamic answer, from the third law, says that the process of cooling becomes infinitely difficult as you approach zero. You'd need an infinite number of steps. The quantum mechanical answer says that even if you could somehow get there, you wouldn't find true stillness waiting for you. There's always zero-point energy, always some residual quantum motion that can never be removed. The destination you're trying to reach doesn't exist in the way you imagined it. It's a mirage that recedes as you approach. But let me tell you about the people who got close, because the story of extreme cooling didn't end with Kamerlingh Onnes and his liquid helium. It was just getting started. After Kamerlingh Onnes liquefied helium and discovered superconductivity, the obvious next step was to go even colder. Liquid helium boils at 4.2 Kelvin, but by pumping on the liquid, lowering the pressure above it so that the most energetic atoms escape as gas, carrying away energy and leaving the remaining liquid cooler, you can get down to about 1 Kelvin, maybe a bit lower. But that's where the technique hits a wall. Below about 1 Kelvin, there's so little thermal energy left in the helium that pumping becomes ineffective. You're trying to squeeze blood from a stone. So physicists needed a new trick, and in the 1920s and 30s, they found one. It was called adiabatic demagnetization, and it's a beautifully clever technique that exploits the magnetic properties of certain materials to achieve cooling far below what liquid helium alone can provide. Here's how it works, and bear with me, because the mechanism is actually quite elegant once you see it. Imagine you have a piece of material, a paramagnetic salt, typically something like gadolinium sulfate or cerium magnesium nitrate, whose atoms have tiny magnetic moments, like tiny bar magnets. At normal temperatures, these magnetic moments are pointing in random directions, jumbled every which way, because thermal energy shakes them around randomly. Now you apply a strong external magnetic field. The magnetic moments align with the field. They snap into order, all pointing the same direction, like iron filings near a magnet. This process releases heat, because you're forcing order onto a system that was disordered, and the energy associated with that disorder has to go somewhere. It comes out as heat. You let that heat dissipate into the liquid helium bath surrounding the salt, so the salt stays at the temperature of the helium bath. Now, and here's the clever part, you thermally isolate the salt from the helium bath. You cut the thermal connection, and then you slowly, carefully, turn off the magnetic field. The magnetic moments, no longer held in place by the external field, want to spring back to their random, disordered state. But randomizing requires energy. You need to increase the disorder, and that takes thermal energy from somewhere. And since the salt is now isolated from everything else, the only place it can get that energy is from its own thermal motion. So the atoms slow down. Their kinetic energy decreases. The temperature drops. The salt gets colder. It's essentially like a game of musical chairs with energy. You use the magnetic field to create order while you're connected to a cold bath that absorbs the released energy. Then you disconnect from the bath and remove the field, and the system disorders itself at the expense of thermal energy, getting colder in the process. You've effectively traded magnetic order for thermal order and come out ahead on temperature. Using this technique, physicists in the 1930s and 40s pushed temperatures down to thousandths of a Kelvin, millikelvins. Temperatures of 0.001 Kelvin, 1,000 times colder than liquid helium. And they did it with nothing fancier than magnets, specially chosen salts, and liquid helium. It was elegant, simple in concept, and stunningly effective. Now let me add a layer to this picture. The technique of adiabatic demagnetization was actually first proposed theoretically by two physicists working independently, Peter Debye in the Netherlands and William Guyot at Berkeley, in the mid-1920s. Guyot was particularly determined to put the theory into practice. He was a meticulous, patient experimentalist who spent years building the apparatus to carry out the first magnetic cooling experiments. In 1933, Jocko and his student D.P. McDougall finally achieved it. They cooled a sample of gadolinium sulfate to about 250 millikelvins, a quarter of a degree above absolute zero. It was a triumph. Guyot won the Nobel Prize in Chemistry in 1949 for his work on the behavior of substances at extremely low temperatures. What's beautiful about adiabatic demagnetization is how clearly it illustrates the back-and-forth game of cooling. You create order in one dimension, magnetic alignment, while getting rid of the heat of ordering. Then you release that constraint and let the disorder creep back in. But this time, the cost of disorder is paid by the thermal energy of the atoms. It's a two-step dance: order, then disorder, and each cycle leaves the system a little colder than before. You can repeat this process multiple times, each cycle shaving off another fraction of the remaining temperature. But each cycle yields diminishing returns. The first cycle might cut the temperature in half. The next cycle cuts it by a quarter, then an eighth, then a 16th. The steps get smaller and smaller, approaching zero but never arriving. There's the third law again, hiding inside the practical mechanics of the experiment. But the really exciting cooling breakthrough came later, and it came from a completely unexpected direction. Not from magnets or gases, but from optics, from lasers. In the 1970s and 80s, a group of physicists began exploring a wild idea that you could use laser light to cool atoms. This sounds completely counterintuitive. Lasers are usually associated with heating things up, with cutting and welding and burning and zapping. How could a laser make something colder? The trick is fiendishly clever, and it relies on the way atoms absorb and re-emit photons of light. Here's the basic idea, and it's worth going through carefully because it's one of the most beautiful applications of quantum mechanics ever devised. Imagine an atom moving toward a laser beam. The laser is tuned to a frequency that's just slightly below the natural absorption frequency of the atom, slightly redder than the color the atom likes to absorb. If the atom were sitting still, it would barely notice the laser. The light would be the wrong color. But because the atom is moving toward the laser, the Doppler effect shifts the light to a slightly higher frequency from the atom's perspective, exactly the way an ambulance siren sounds higher pitched when it's coming toward you. So the atom sees the laser light as being exactly the right frequency, the right color, and it absorbs a photon. Now, when the atom absorbs that photon, the photon carries momentum. It gives the atom a little kick, a push, in the direction opposite to its motion, backward, slowing it down. A moment later, the atom re-emits a photon as it drops back to its original energy state. But here's the key. It emits that photon in a random direction, sometimes forward, sometimes backward, sometimes up, sometimes to the side. Over many, many cycles of absorption and re-emission, the pushes from the absorbed photons always point the same way, against the atom's motion, while the re-emitted photons push randomly in all directions, and those random pushes average out to zero. The net effect is a one-directional braking force. The atom slows down, and slowing down means cooling down. You're using light itself as a brake, decelerating atoms without touching them, without putting them in contact with anything cold. You're just shining carefully tuned light on them and letting the physics do the rest. If you arrange 6 laser beams, 2 from each direction, forming 3 perpendicular pairs, you can slow atoms down in all 3 dimensions simultaneously. An atom moving in any direction encounters a laser beam that's Doppler shifted to just the right frequency for absorption, gets a backward kick, and slows down. The result is a region in the center of the apparatus, where atoms are slowed and trapped by light. Stephen Chu, who led much of this pioneering work, called it optical molasses, because the atoms moved as if they were swimming through thick syrup, always being slowed, never being sped up. The name optical molasses wasn't just poetic, it was physically apt. The laser-cooled atoms really did behave as if they were swimming through something thick and viscous. But even optical molasses has a limit. There's a minimum temperature you can reach with simple Doppler cooling, called the Doppler limit, and it's set by the natural line width of the atomic transition you're using. For most atoms, the Doppler limit is around 100 microkelvins, 100 millionths of a degree. That's fantastically cold, but physicists wanted to go colder. And here's where the story takes one of those wonderful turns, where experiment outruns theory. When researchers actually measured the temperature of their laser-cooled atoms, they found something surprising. The atoms were colder than the Doppler limit, significantly colder. This wasn't supposed to happen. The theory said there was a floor, and the atoms had somehow gone below it. For a while, nobody understood how. It was Claude Cohen-Tanagi, working in Paris, who figured it out. He showed that a more subtle mechanism was at work, one involving the complex interplay between the atom's internal quantum states and the polarization gradients in the light field created by overlapping laser beams. This mechanism, which came to be called Sisyphus cooling, after the mythological king condemned to roll a boulder up a hill for eternity, only to have it roll back down each time, works differently from simple Doppler cooling. In Sisyphus cooling, atoms climb potential energy hills created by the light field, losing kinetic energy each time, and then get optically pumped back to the bottom of a new hill to climb again. Each climb costs them speed. Each optical pumping resets them to start another climb. The atoms are like tiny Sisyphus figures, forever laboring uphill, and each time they reach the top and get knocked back to the bottom, they've lost a little more energy. Sisyphus cooling can reach temperatures of a few microkelvins, tens of times colder than the Doppler limit, and it's what made the final push to Bose-Einstein condensation possible. Without it, there would have been a gap between the coldest laser-cooled atoms and the temperatures needed for condensation. Sisyphus cooling bridged that gap, and the name, combining ancient Greek myth with cutting-edge quantum optics, captures perfectly the beautiful absurdity of modern physics. This technique, called Doppler cooling or laser cooling, was developed primarily by Stephen Chu, Claude Cohen-Tanagi, and William Phillips, who shared the 1997 Nobel Prize in Physics for their work, and it allowed physicists to reach temperatures that had been completely unimaginable just a few years earlier. Microkelvins, millionths of a degree above absolute zero, and with further refinements, techniques with names like Sisyphus cooling and sub-Doppler cooling, even nanokelvins, billionths of a degree. Think about that for a moment. A billionth of a degree above absolute zero, the coldest naturally occurring place in the universe that we know of is the Boomerang Nebula, a cloud of gas and dust about 5,000 light-years from Earth, where the rapid expansion of gas has cooled it to about 1 Kelvin. Deep space itself, the void between galaxies, sits at about 2.7 Kelvin, the temperature of the cosmic microwave background radiation, the cooled-down afterglow of the Big Bang. And in laboratories on Earth, in rooms in Boulder, Colorado, and Paris, France, and Cambridge, Massachusetts, scientists have created temperatures billions of times colder than the Boomerang Nebula, billions of times colder than the void of deep space, colder than anything that exists anywhere in the natural universe. As far as we know, humanity, on this little rocky planet, has created the coldest conditions that have ever existed in the 13.8 billion year history of the cosmos. Not out in the depths of space, not in some exotic environment, but in a lab, using lasers and magnets and vacuum chambers, and extraordinary ingenuity. And at these fantastically low temperatures, matter does something that perfectly illustrates the quantum nature of reality. It forms a state of matter that was predicted 70 years before it was first observed. It's called a Bose-Einstein condensate, and it's one of the most remarkable things in all of physics. The story starts with two people, Satyendra Nath Bose, an Indian physicist working in Dhaka in what is now Bangladesh, and Albert Einstein. In 1924, Bose was working on the statistical mechanics of photons, the particles of light. He came up with a new way of counting quantum particles that differed subtly, but crucially, from the classical approach. He sent his paper to Einstein, who immediately recognized its importance. Einstein translated the paper from English into German, helped get it published in a prestigious German journal, and then extended Bose's ideas from photons to atoms. What Einstein realized was that if you cooled a gas of certain types of atoms, specifically atoms that belong to the class of particles called bosons, down to extremely low temperatures, something extraordinary would happen. The atoms, which at higher temperatures behave as distinguishable individuals bouncing around independently, would begin to overlap. Their quantum wave functions, the mathematical descriptions of where each atom might be found, would spread out as the temperature dropped. Each atom would become less like a particle and more like a fuzzy wave, its position increasingly uncertain, and at a critical temperature, an absurdly, spectacularly low one, those wave functions would overlap so completely that the atoms would lose their individual identities entirely. They'd merge into a single quantum entity, all of them occupying the same quantum state, behaving as one giant superatom. It's like, imagine a crowd of people walking around a park. At high temperatures, they're all going their own way, each person a distinct individual, their paths crossing randomly. As the temperature drops, they start moving more slowly. They become more spread out, less sharply defined, like each person is becoming blurry around the edges. And then, below a critical temperature, all the people merge into a single vast figure that fills the entire park. Not a crowd anymore, one entity, one wave. It's a strange analogy, honestly, and it breaks down if you push it, but the physics is real. And in 1995, 71 years after Einstein's prediction, two teams finally created a Bose-Einstein condensate in the laboratory. Eric Cornell and Carl Wieman at Gila in Boulder, Colorado, used a cloud of rubidium atoms cooled to about 170 nanokelvins, 170 billionths of a degree above absolute zero. A few months later, Wolfgang Ketterle at MIT did the same with sodium atoms. All three shared the 2001 Nobel Prize in Physics for this achievement. The creation of a Bose-Einstein condensate was a triumph of experimental physics, and it was only possible because of the laser cooling techniques developed in the previous decade. The process is a multi-stage relay race of cooling methods. You start with a cloud of atoms at room temperature. You slow them with lasers. You trap them in a magnetic field. You cool them further with more sophisticated laser techniques. And then, for the final push, you use evaporative cooling, essentially letting the most energetic atoms escape from the trap, the way the hottest molecules escape from a cup of hot coffee, leaving the remaining atoms colder. Each technique picks up where the last one left off, each one effective in a different temperature range, each one carrying the baton a little further toward a finish line that can never quite be crossed. And the Bose-Einstein condensate itself is a thing of strange beauty. It's a tiny cloud of atoms, usually a few million, invisible to the naked eye, but it behaves as a single quantum object. If you send two condensates toward each other, they don't collide like two balls of gas. They create interference patterns, like two overlapping ripples on a pond, because they're not really separate objects anymore. They're quantum waves, and quantum waves interfere. You can literally see quantum mechanics made visible, well, with the help of some imaging equipment, in a Bose-Einstein condensate. Let me tell you about one more exotic state of matter, because it illustrates just how rich and strange the physics of extreme cold continues to be. It's called a fermionic condensate, and its creation is one of the great achievements of 21st century physics. Remember how I mentioned that there are two fundamental types of particles in nature, bosons and fermions? Bosons are the sociable ones, with integer spin, 0, 1, 2, and they love to pile into the same quantum state. That's what makes Bose-Einstein condensation possible. Fermions, on the other hand, are the antisocial ones, with half-integer spin, 1/2, 3/2, and they obey the Pauli exclusion principle, which flatly prohibits two identical fermions from occupying the same quantum state. Electrons are fermions, So are protons, and neutrons, and the atoms of many common elements. So you might think you can't make fermions condense. If they refuse to pile into the same state, how can they form a condensate? But nature, as always, is cleverer than our first intuitions. In 2004, Deborah Jin and her team at Gila in Boulder, Colorado, figured out how to make fermions pair up. Two fermions, bound weakly together, create a composite particle that acts like a boson, and those composite bosons can condense. It's analogous to what happens in superconductors, where individual electrons, fermions, pair up into so-called Cooper pairs through their interaction with the vibrations of the crystal lattice. Cooper pairs behave as bosons and condense into a superconducting state. Jin created the same kind of pairing, but in a gas of ultra-cold potassium-40 atoms at temperatures around 50 nanokelvins. Deborah Jin was a remarkable scientist, quiet, intense, deeply creative, and enormously generous as a mentor and collaborator. She was one of those rare experimentalists who combined extraordinary technical skill with deep physical intuition. She didn't just build apparatus, she understood what the atoms were telling her. Tragically, she died of cancer in 2016, at the age of just 47. The physics community lost one of its brightest stars. She never received the Nobel Prize that many felt was inevitable, because the Nobel can only be awarded to the living. The creation of fermionic condensates opened up a vast new landscape of physics. By tuning the interactions between atoms, using magnetic fields to adjust how strongly they attract or repel each other, physicists can now simulate conditions that exist inside neutron stars, inside exotic superconducting materials, inside environments that are completely inaccessible to direct experiment. Ultra-cold atomic gases have become a kind of quantum simulator, a laboratory where you can dial up the physics of extreme environments and watch what happens. It's as if you had a knob that could tune the laws of physics themselves. Now, you might be wondering, just how close to absolute zero have we actually gotten? What's the record? As of the early 21st century, the coldest temperatures ever achieved in a laboratory are on the order of a few hundred picokelvins. That's trillionths of a degree above absolute zero. In 2003, a team at MIT led by Ketterle reached about 450 picokelvins using a sodium Bose-Einstein condensate. Other groups have achieved comparable or even lower temperatures since then, including experiments aboard the International Space Station in the Cold Atom Lab, where microgravity allows ultra-cold atoms to be studied without the complications of gravity pulling them to the bottom of their trap. 450 picokelvins. Let me try to put that in perspective. Absolute zero is 0 Kelvin. Room temperature is about 300 Kelvin. The surface of the sun is about 5,800 Kelvin. So we live at 300. The sun lives at nearly 6,000. And these scientists have gotten their atoms to 0.0000000000045. That's so close to zero that the ratio between their temperature and room temperature is like comparing the width of a single atom to the distance from here to the nearest star. It's essentially zero, for all practical purposes, but it's not zero. It never will be zero. That last infinitesimal gap remains and will always remain. The laws of physics guarantee it. Let me take you a little deeper into why. Let's really sit with the third law and understand the mathematical structure behind this impenetrable barrier. The third law, as formulated by Nernst and later refined by Max Planck, Francis Simon, and others, has several equivalent formulations. One way to state it is this: it is impossible to reduce the temperature of a system to absolute zero in a finite number of steps. Each cooling step gets you closer, but the steps get smaller and smaller, like Zeno's paradox. You're always halving the remaining distance, always closing in, never arriving. Here's another way to think about it, one that connects to the deeper mathematics. Every cooling process involves transferring entropy from the system you're cooling into the environment. You're making your system more ordered, lower entropy. By making the environment less ordered, higher entropy. The total entropy of the universe increases as the second law demands. But as the system's temperature approaches zero, its entropy approaches zero too. And you can't transfer entropy out of something that already has nearly no entropy to give. It's like trying to squeeze water out of a nearly dry sponge. Each squeeze yields less and less. You can keep squeezing forever, and you'll keep getting tiny droplets, but you'll never get the sponge perfectly dry. And there's yet another perspective, one that connects to information theory in a deep and satisfying way. Temperature, entropy, and information are intimately related. The entropy of a system is related to how much information you'd need to specify the exact microscopic state of that system. A high-entropy system has many possible microstates, and you'd need a lot of information to pin down which one it's actually in. A low-entropy system has fewer possible microstates, and you need less information. At absolute zero, a perfect crystal has zero entropy. That means there's only one possible microstate. You know exactly how every atom is arranged. You have complete, perfect information about the system. But acquiring complete information about a physical system, knowing everything about it down to the last quantum number, requires infinite precision. And in quantum mechanics, through the uncertainty principle, infinite precision simply isn't available. It's prohibited by the fundamental structure of the theory. Complete information is unattainable, and therefore, zero entropy is unattainable, and therefore, absolute zero is unattainable. The chain of logic is airtight, so the unreachability of absolute zero connects to the impossibility of having perfect information about a quantum system. It connects to the Heisenberg uncertainty principle, to the second law of thermodynamics, to the nature of entropy itself. These are all different facets of the same deep truth about reality. Different windows looking into the same room. Let me slow down here and talk about something that I find fascinating. The deep parallel between absolute zero and the speed of light. Because these two limits, which seem completely unrelated on the surface, are actually twin expressions of the same underlying truth about the universe. The speed of light in a vacuum, about 300 million meters per second, or about 670 million miles per hour, is the upper limit of speed. No object with mass can reach it. As a massive object approaches the speed of light, its effective mass increases, and it takes more and more energy to accelerate it further. The closer you get, the harder it becomes. To reach the speed of light exactly, you would need infinite energy. The barrier is asymptotic. You can approach it ever more closely, but you can never cross it. Sound familiar? The exact same structure applies to absolute zero. The closer you get to zero temperature, the harder it becomes to get any closer. Each increment of cooling requires more effort, more energy, more sophistication. To reach zero exactly, you would need an infinite number of steps, which is just another way of saying you'd need infinite resources. These two limits define the boundaries of the physical world. The speed of light is the ceiling of motion. Absolute zero is the floor of temperature. Together, they form a kind of box, a container of possibilities within which all physical processes take place. Every object in the universe exists somewhere between these extremes, warmer than absolute zero and slower than light. And both limits arise from the same kind of mathematical structure. In relativity, the speed of light appears as a limiting velocity because of the way space-time is structured. The geometry of the universe makes light speed special. In thermodynamics, absolute zero appears as a limiting temperature because of the way entropy is structured. The statistical mechanics of the universe makes zero temperature special. In both cases, the limit isn't a wall you bang into. It's a horizon that recedes as you approach it, always there, always visible, always just out of reach. There's even a direct mathematical connection. In certain formulations of statistical mechanics, temperature enters the equations in a way that's analogous to how velocity enters the equations of special relativity. Just as there's a rapidity in relativity that can increase without bound, even as the velocity asymptotically approaches the speed of light, there's an analogous quantity in thermodynamics, a kind of coldness parameter that can increase without bound, even as the temperature asymptotically approaches zero. The mathematics has the same shape, the same architecture. It's as if the universe uses the same blueprint for all its limits. This is one of those deep patterns that makes physicists believe that beneath all the different branches of physics, thermodynamics, relativity, quantum mechanics, there's a single, unified framework waiting to be discovered. A theory of everything that would show why all these limits exist, why they have the same structure, why the universe is built with guardrails at the extremes. We don't have that theory yet, but the hints are everywhere, and the unreachability of absolute zero is one of the most elegant. And here's one more mind-bending twist that I can't resist sharing, because it shows just how strange temperature really is once you dig into its statistical foundations. It turns out that, in a very specific and carefully defined sense, there are temperatures below absolute zero, negative temperatures, and they're not what you think. This sounds like it contradicts everything I've been saying, but bear with me. Negative absolute temperatures don't mean colder than absolute zero. They actually mean hotter than anything with a positive temperature. I know, that sounds completely insane, but it follows rigorously from Boltzmann's definition of temperature as the relationship between energy and entropy. Remember, temperature is related to how entropy changes when you add energy. For a normal system at a positive temperature, adding energy increases the entropy. There are more ways for the atoms to arrange themselves. The hotter the system, the less each additional bit of energy increases the entropy. At infinite temperature, adding energy doesn't change the entropy at all. You're already at maximum disorder. But here's the weird part. In certain carefully engineered systems, like a collection of atomic spins in a magnetic field, where there's an upper bound on the energy each spin can have, you can create a situation where adding energy actually decreases the entropy. The system has been pushed beyond maximum disorder into a kind of inverted state where it's becoming more ordered as you add energy. The temperature, defined through the entropy-energy relationship, becomes negative. And a negative temperature system isn't cold. It's incredibly hot. Hotter than any positive temperature. If you put a negative temperature system in contact with a positive temperature system, heat flows from the negative temperature system to the positive temperature one, just as heat flows from hot to cold. The negative temperature system is the hotter one. The temperature scale, properly understood, goes 0, positive, positive infinity, negative, and back toward 0 from the other side. It's a circle, not a line. And absolute zero sits at the inaccessible point where the circle meets itself, unreachable from either direction. This was first achieved experimentally in the 1950s by Edward Purcell and Robert Pound, using nuclear spin systems, and more recently, in 2013, by a team in Munich that created a negative temperature state in a gas of potassium atoms trapped in an optical lattice. It's exotic, it's counterintuitive, and it beautifully illustrates that our everyday intuition about temperature, hotter means higher number, Colder means lower number, is just an approximation of something far more subtle and strange. But the key point for our story remains. Even with negative temperatures, absolute zero itself is unreachable. It sits at the boundary, the singularity, the point where the temperature function breaks down. You can't reach it from the positive side, and you can't reach it from the negative side. It's the absolute, inviolable floor of the physical world. Now, I want to take you somewhere unexpected, because the story of absolute zero doesn't just live in physics laboratories and university departments. It has tendrils that reach into cosmology, into the history of the universe, and into the far, far future. Think about the early universe. In the first fraction of a second after the Big Bang, the universe was unimaginably hot. Temperatures in the trillions of degrees. All matter was a soup of quarks and gluons, too hot for even protons and neutrons to exist as stable particles. As the universe expanded, it cooled. Particles formed, nuclei formed, atoms formed. About 380,000 years after the Big Bang, when the temperature dropped to about 3,000 Kelvin, stars ignited, galaxies assembled, and the background temperature of the universe, the temperature of empty space itself, has been dropping ever since. Right now, the cosmic microwave background radiation, that faded afterglow of the Big Bang, stretched by the expansion of the universe from visible light to microwave radiation, sits at about 2.725 Kelvin. That's the average temperature of the universe, the temperature of the void between galaxies, and it's been dropping steadily as the universe expands and stretches and thins. Now, project that forward, way forward, billions and trillions and quadrillions of years into the future. The universe will keep expanding. The stars will burn out, one by one. First, the massive blue giants, then the mid-sized yellow stars like our sun. Then finally, far in the future, the small red dwarfs, the most frugal stars, burning their hydrogen fuel so slowly that the smallest of them will last for trillions of years. But eventually, they'll all go out. The last stellar ember will flicker and die. The universe will be dark, and after the stars die, the remnants, white dwarfs, neutron stars, black holes, will persist for a while. But even they are not eternal. White dwarfs will cool over quadrillions of years, fading from white to red to brown to black. Black holes will slowly evaporate through Hawking radiation, a quantum mechanical process by which black holes emit particles and gradually shrink, over timescales so vast that the numbers lose all meaning. The largest black holes will take something like 10 to the 100th power years to evaporate. That's a 1 followed by 100 zeros, an incomprehensibly long time. And all the while, the temperature of the universe will keep dropping, asymptotically approaching zero, getting closer and closer, but, and here's the beautiful connection to our story, never reaching it, never crossing that final threshold. The same law that prevents a physicist in a laboratory from reaching zero applies to the entire cosmos. The universe itself is engaged in an eternal, asymptotic approach to a limit it can never reach. There's something quietly magnificent about that. The entire universe, all of existence, bound by the same elegant constraint that frustrates the most sophisticated cryogenics lab on Earth. The third law of thermodynamics doesn't just apply to crystals and gases and laboratory experiments. It applies to everything. It's a cosmic law, as deep and as inviolable as the conservation of energy or the speed of light. Let me bring things around to some of the modern applications and cutting-edge research, because the science of extreme cold isn't just about reaching records or testing abstract theories. It has real, practical, world-changing applications that are shaping technology right now. Superconducting magnets are everywhere. Every MRI machine in every hospital runs on a superconducting magnet, a coil of wire cooled to about 4 Kelvin with liquid helium, carrying a persistent current that generates the strong, stable magnetic field needed to image the inside of your body without cutting you open. If you've ever had an MRI, you've been inside a piece of technology that only works because of what Kamerlingh Onnes discovered over a century ago. Particle accelerators like the Large Hadron Collider at CERN use over 1,600 superconducting magnets, cooled to 1.9 Kelvin, colder than outer space, to steer beams of protons around a 27-kilometer ring at 99.99999% of the speed of light. The entire LHC is bathed in nearly 100 tons of superfluid helium. It's one of the coldest, large-scale environments ever created by humans. Speaking of helium, and this is a tangent, but an important one, the element that makes most ultra-cold research possible is itself becoming scarce, and the irony is almost too perfect. Helium is the second most abundant element in the universe. It makes up about 24% of all the matter you can see, by mass. But on Earth, it's rare. It doesn't occur naturally in the atmosphere in any significant quantity, because it's so light that it escapes Earth's gravity. The helium we use comes from underground deposits, produced by the radioactive decay of heavy elements like uranium and thorium deep in the Earth's crust. It seeps up through the rock and gets trapped in certain geological formations, often alongside natural gas. For decades, the United States maintained a strategic helium reserve, a vast underground storage facility near Amarillo, Texas, in a porous rock formation called the Bush Dome. It was established after World War I, when helium was recognized as strategically important for military airships. The reserve grew through the 20th century, accumulating over 1 billion cubic meters of helium at its peak. But beginning in the 1990s, the U.S. government decided to sell off the reserve, and it's been drawn down significantly. There have been periodic global helium shortages in 2012, 2019, and beyond that have affected everything from MRI machines in hospitals to birthday party balloons. The scientific community has been sounding the alarm for years. Nobel laureate Robert Richardson warned in 2010 that helium should cost far more than it does, that it's being squandered on frivolous uses while the supply dwindles. And here's the thing that makes it uniquely concerning. You can't make more. You can't synthesize helium economically. Once it's released into the atmosphere, it drifts up and away, ultimately escaping into space. Every helium balloon that floats off at a birthday party is sending a tiny bit of an irreplaceable element on a one-way trip out of our atmosphere. The element that allows us to explore the coldest temperatures in the universe, to run MRI machines, to operate the world's most powerful particle accelerators and quantum computers. That element is slowly, inexorably leaking away from our planet. There are efforts underway to find new helium sources, to improve recycling and recapture, and to develop technologies that use less helium or substitute other coolants where possible. But for the foreseeable future, liquid helium remains indispensable for cutting-edge cold science, and its scarcity is a genuine concern for the future of the field. And then there's quantum computing, perhaps the most exciting technological frontier of the 21st century. The most common type of quantum computer, the superconducting quantum computer, requires extreme cold to function. The quantum bits, qubits, need to be cooled to about 10 to 15 millikelvins. That's thousandths of a degree above absolute zero. At that temperature, the thermal noise that would scramble the delicate quantum information is suppressed enough for the qubits to maintain their fragile quantum states long enough to perform calculations. The refrigerators used for quantum computing are called dilution refrigerators, and they use a mixture of two isotopes of helium, helium-3 and helium-4, to achieve continuous cooling through a quantum mechanical process. Helium-3 dissolves into helium-4 in a way that absorbs heat, much like salt dissolving in water produces a cooling effect. By continuously cycling helium-3 through this dissolving process, the refrigerator can maintain temperatures of a few millikelvins indefinitely. These machines are marvels of engineering. Tall, chandelier-like structures of gold-plated copper discs and stainless steel tubes, humming quietly in climate-controlled rooms, maintaining temperatures a few thousandths of a degree above the coldest possible point. And there's one more application that I find particularly beautiful: precision timekeeping. Ultra-cold atoms are the basis of the most precise clocks ever built. Optical lattice clocks, which trap atoms in a grid made of intersecting laser beams and measure the frequency of specific atomic transitions, keep time so accurately that they wouldn't gain or lose a single second in 15 billion years. That's longer than the current age of the universe. These clocks are so precise that they can measure the gravitational redshift predicted by Einstein's general relativity, the effect where clocks tick slower in stronger gravitational fields, over a height difference of just a single centimeter. The atoms need to be ultra-cold so that their thermal motion doesn't blur the spectral lines being measured. Colder atoms mean sharper measurements, and sharper measurements mean better clocks, and better clocks mean better physics, better navigation, and a deeper understanding of space-time itself. So the quest for absolute zero isn't just an abstract pursuit of a number. It's yielding tools and technologies that are reshaping our understanding of the universe and our ability to build transformative things. Let me bring this journey toward a close now, and let's come back to where we started. The question was deceptively simple: why can't we reach absolute zero? And the answer, as we've seen, is rich, multi-layered, and beautiful. There's the thermodynamic answer. The third law says that reaching absolute zero would require an infinite number of cooling steps. Each step removes some energy, but each subsequent step removes less than the last. You're always having the remaining distance, approaching but never arriving. It's built into the mathematics of entropy and energy transfer. There's the quantum mechanical answer. The Heisenberg uncertainty principle guarantees that particles always retain zero-point energy, a minimum amount of motion that can never be removed. Even at absolute zero, atoms aren't still. They're jiggling with an irreducible quantum motion that's not thermal energy, not the result of heat, but a fundamental consequence of the wave-like nature of matter. There's the statistical mechanical answer. Temperature is about how energy is distributed among particles. At absolute zero, there's only one possible distribution: the ground state. And the system is maximally ordered. But reaching perfect order requires removing every last trace of thermal energy. And each trace becomes harder to extract as you approach zero. There's the information theoretic answer. Zero entropy means complete information about every particle in the system, and quantum mechanics, through the uncertainty principle, puts a fundamental limit on how much you can know. Complete information is unattainable. Therefore, zero entropy is unattainable. Therefore, absolute zero is unattainable. And there's the cosmological answer. The universe itself, expanding and cooling since the Big Bang, will asymptotically approach absolute zero over incomprehensible timescales, but it will never arrive. The same laws that constrain a laboratory constrain the cosmos. All of these answers are really the same answer wearing different masks. They're all consequences of the same deep structure of reality, a structure that includes quantum mechanics, thermodynamics, and the nature of information. They're all telling us the same thing in different languages. There is a floor, and it is unreachable, not because we're not clever enough, but because the universe is built that way. And I think there's something deeply comforting about that. Not frustrating, comforting. Because it means the universe has structure. It has rules. It has limits that aren't arbitrary, but arise from the deepest principles we've ever discovered. The unreachability of absolute zero is not a failure. It's a feature, a signpost pointing toward the fundamental architecture of reality. Think about the people we've met along the way. Rumford, watching cannon barrels being bored and realizing heat isn't a substance. Carnot, working out the limits of heat engines in Napoleonic France, dying of cholera at 36 before he could see his ideas change the world. Clausius, uncovering the mathematical structure of entropy. Lord Kelvin, laying down the absolute temperature scale. Boltzmann, seeing deeper than anyone into the statistical nature of heat and paying a terrible personal price for being ahead of his time. Nernst, the brash chemist, with his walrus mustache and his world-changing heat theorem. Kamerlingh Onnes, patient and methodical in his frozen laboratory in Leiden, liquefying helium and stumbling onto superconductivity. Kapitsa, Allen, and Missener, discovering the liquid that climbs walls and flows forever. Bose and Einstein, predicting a new state of matter that wouldn't be seen for 7 decades. Chu, Cohen-Tanoji, and Phillips, taming laser light itself to cool atoms to millionths of a degree. Cornell, Wieman, and Ketterle, creating matter that behaves as a single quantum wave. Every one of them pushed a little closer to zero. Every one of them learned something astonishing about the nature of matter and energy in the process. And every one of them ran into the same wall, a wall made not of stone or steel, but of logic and quantum mechanics and the fundamental structure of reality itself. The wall at absolute zero isn't something you can see or touch. It's a wall made of mathematics, of the way the equations work, of the way the universe keeps its own accounts. You can approach it, and the approach is where all the wonder lives, where superconductors and superfluids emerge, where Bose-Einstein condensates form, where quantum mechanics reveals itself in all its bizarre and beautiful glory. The approach is where the physics happens. The destination, true zero, is forever out of reach. And that's not a flaw, that's the design. Because the universe, at its deepest level, is never still, never empty, never truly silent. Even in the coldest place you could ever create, even in the most perfect vacuum, even in the most isolated system conceivable, something is always happening. Quantum fields are fluctuating. Virtual particles are flickering in and out of existence. Zero-point energy is humming along, a quiet bass note beneath everything else. And right now, as you lie there, all of this is happening inside you. Every atom in your body is vibrating with thermal energy, and below that, with zero-point energy that will never go away. The protons and neutrons in your atoms are held together by forces that have their own quantum fluctuations. The electrons in your cells are obeying the Pauli exclusion principle, stacking up in energy levels, refusing to collapse into a single state. You are, in the most literal sense, a warm thing in a cooling universe, a small island of ordered energy in the vast, expanding expanse of space. The universe has been cooling for 13.8 billion years. The cosmic microwave background has cooled from thousands of degrees to less than 3 Kelvin, and it will keep cooling for billions and trillions of years to come, asymptotically approaching, but never reaching, that impossible, unreachable floor. And somewhere in the far, far future, so far that the numbers become meaningless, so far that every star has burned out and every black hole has evaporated, the universe will be almost immeasurably cold, almost at zero, almost still, almost silent, almost, but not quite, never quite. Because the universe, in its infinite subtlety, has built absolute zero as a limit that cannot be crossed, a horizon that recedes as you approach it, a promise of perfect stillness that is never fulfilled, because the quantum nature of reality guarantees that something is always, always happening, even at the end of time, even at the edge of cold. And there's something peaceful about that, don't you think? The universe is never truly done, never truly finished. There's always one more vibration, one more fluctuation, one more whisper of energy rippling through the vacuum. The story never quite ends. The hum never quite fades to silence. So as you settle deeper into the warmth of your blankets tonight, warmth that is nothing more and nothing less than billions of atoms vibrating and jostling, sharing energy, doing their endless quantum dance. Take a moment to appreciate what temperature really is. It's not just a number on a thermostat. It's the music of atoms, the rhythm of matter, the heartbeat of the universe itself. And at the very bottom of the scale, at the edge of all that's physically possible, there's a note that can never be played, a silence that can never be achieved, a zero that remains forever, just out of reach. The atoms are always dancing, even when they're barely moving at all, even at the coldest place in the cosmos, even at the end of everything, they're still dancing. And that, when you think about it, is one of the most beautiful things physics has ever taught us. The universe is restless, irreducibly, fundamentally, gloriously restless. And no matter how hard you try, no matter how clever your technique, how advanced your equipment, how patient your approach, you can't make it stop, not even close. Well, almost close. Breathtakingly, mind-bogglingly, record-shatteringly close. Close enough that the remaining distance is smaller than anything you can meaningfully imagine, but not there, never there. And maybe that's exactly how it should be. Let that thought settle over you like a blanket. Let the restlessness of the universe, that quiet, eternal hum at the bottom of everything, be something that soothes rather than unsettles, because it means the story isn't over. It means there's always something left to discover, always one more layer to peel back, one more mystery to unravel, one more fraction of a degree to shave away from that unreachable limit. The quest for absolute zero is a quest that will never end, and the journey itself, the beautiful, strange, endlessly surprising journey through the coldest reaches of physics, is the whole point. The atoms are dancing. They always have been. They always will be. Sleep well.